All right, good afternoon, everyone. This is a talk about crypto and usability. There's not going to be anything about math, so stick around. It's going to be interesting, and hopefully everybody can understand. So, I'm Frank Denis. I work on a bunch of different things. The main thing I do right now is build models for computer vision and digital image processing. But what we're going to talk about right now is really about crypto. And crypto means a lot of different things. There's a lot you can do with it. But usually when you think you need crypto for the first time, it's because you need to encrypt stuff. So where do you start? Well, probably with Google. Like how to encrypt stuff in C. And this is what I tried a couple of weeks ago when I was preparing this presentation. And wow, about 3 million results. Sounds good. All right, let's look at what we get on the first page to encrypt stuff. The Kaiser cipher and the Virginia cipher. Well, these are pretty interesting ciphers. I mean, with a pen and paper, they are pretty interesting, but they don't provide any kind of security whatsoever, which is pretty sad. All right, let's keep reading. What do we have on the first page as well? Oh, Stack Overflow. That has to be good. You can use a variant of base64 with a custom alphabet. All right. Next. Or this one is exceptionally strong. Well, half of it doesn't do anything. The function requires a key, but it doesn't even use it. That's terrible. All right. Next. What should I do? A very simple XOR algorithm. I'm using it for some IoT stuff. Well, IoT security is doomed. All right. So you're going to keep reading about crypto, and then you're going to discover a lot of different names, such as this. This is just a very small subset of what you're going to come across. And then, well, this is not enough. You can't encrypt a lot with that, so you have to learn about something else called the mode, and there's a lot of them to choose from. And then it's not enough. A bunch of parameters to choose from as well, such as a key size. And then you're going to encrypt stuff. But it's not secure. You need to add more, like some MAC and some padding and yada yada. That's a lot of stuff to digest just to encrypt stuff. Well, C developers are weird, right? So maybe try something else. How to encrypt stuff in PHP. So apparently everybody recommends something called mcrypt. Scroll. Oh, what the fuck is that? A lot of function names. I don't know what they do. Nothing says encrypt. What am I supposed to use? Well, let's look at the documentation. Well, in CBC mode, you may supply an IV, and to get it, maybe you can just use MD5 of the file name. This is a terrible, terrible, terrible advice. And this is in the official documentation of the library everybody recommends, which hasn't been maintained for a very long time. This is really, really sad. And the thing is, crypto is hard to design, but it's also pretty hard to use. And, of course, this leads to security disasters. But developers are not to blame. And the reason for that is that crypto is usually just a very small piece in your application. You just need it for something specific, and then you go back to what you like to do and what the application is actually supposed to do. And like, if you want to play some music, you get some audio library, and you call a function which is called like load, and then play, and poof, you get some music. And people expect the same thing from a crypto library. But with crypto, this is not the case. You have to understand how everything works under the hood. This is not normal. And this is why we saw so many disasters. So maybe if we take a look at something more recent, maybe they learned from history, right? Web Crypto API. Shit. This is exactly just like mcrypt. Not any better. That's pretty sad. All right. In 2010, there was a library called Knuckle, or Thought, which was quite a game changer, and it was really focused on high-speed cryptography and improving usability. Its API was really simple, hard to use the wrong way. It was designed by experts, such as Daniel Bernstein, so it was great, right? But a couple of years later, nobody was using it. Well, some project did, but really just a couple. That's pretty sad. I mean, state-of-the-art cryptography, very easy to use, nobody's using it. And the reason for that is that whereas the API itself was really good, actually using this library in your applications was kind of tricky. So a couple years later, this pretty nice guy called Tony Ascieri was like, hey, what about using the NiCol API, but with a very simple implementation, really dumb functions, non-optimized functions, but this is going to be code that anybody can use in any language, on any platform. It will be great, right? And incidentally, this is something I had been working on for quite some time. So a couple days later, I was like, hey, look, this is on GitHub. It's called Sodium. Just a disclaimer, this is not a talk about Sodium. What I'm going to talk about now can apply to any crypto library. It just happens that Sodium has an API that has changed a lot over time. So I think this is a good example to look at. And I just want to explain why this API has changed, how, and some takeaways from its past 4 years of existence. So essentially, Sodium was a slow version of NiCol, and everybody liked it. That's pretty nuts, right? But actually what it means is that in crypto, the first problem to solve was not security. That's been solved a long time ago, actually. Not speed, which is the main thing cryptographers are focused on. This is really usability. And if you want to design crypto library today, you have to keep in mind that people use a lot of different platforms and languages. Like if you write a secure messenger, it's expected that your messenger is going to be working on Mac, on Windows, on any mobile device. And a platform which is really, really important and then people have overlooked for many, many years is JavaScript and WebAssembly. Because today, everybody is using React Native and Wix and Electron and things like that. So it should really be a first-class citizen, even for a crypto library. So Sodium supports all of this, which is maybe why people are actually using it a lot. And if you design an API, so it's for crypto or whatever, and you want people to use it, it's really important to not use specific things from a specific language. Like in C, macros are really useful, but if you try to use macros in Python, well, good luck with that. So try to stick to some generic things, the generic functions, even for constants, so that your code can actually be used from any language. Package maintainers are your best friends, and this is very important. Like today, nobody wants to actually compile stuff anymore. People just want to use apt-get or pacman or whatever. And you can't possibly maintain packages for all possible distributions and operating systems out there. So you need help. And the best way you can get help from these people is actually to make their jobs easier. So stick to very boring build systems, such as AutoTools. AutoTools suck, but everybody knows how to use it, and package maintainers can just apply recipes they know in order to build packages for your stuff. So don't be too smart if you want people to help you. So the key idea behind NiCol and then Sodium is to actually not expose low-level operations. Like for hashing, instead of exposing a function which is like SHA-256, you expose a function that says hash, or encrypt, verify, sign. So you express what you want to do, not a specific function name to do it. And you keep the number of parameters down to a minimum. As a designer, you choose safe defaults, and it's going to make application developers' life easier, especially if they're not very familiar with crypto. And it's going to be more difficult to shoot yourself in the foot. Nobody reads the documentation. And when you actually have to solve a problem really quick, you really don't want to understand how everything works and read the documentation of every single function. You just want to copy and paste stuff. So maybe you're going to go to Stack Overflow first, and we saw that it might not be a good idea. So in the documentation of your library, it might be a good idea to actually start with code snippets. Even before describing what the function does and how it works, start with code snippets that people can actually copy and paste. And actually just looking at this kind of code is actually a very, very good way to understand how everything works. So yeah, that's a way to structure your documentation so that people can get started really quickly. And more importantly, watch how people use your APIs in their own projects. Maybe you had something in mind, but people are going to use your code in a very different way that you didn't think about. And watch yourself struggle while using your own code as well. So, for example, when the first version of Sodium was released, and even with Knuckle, for the few projects using them, I just looked at these projects, and I saw that pretty much everyone was actually writing wrappers around key functions from these libraries, because the API was not exactly a good fit for these applications. So that's pretty interesting. And if you look at OpenSSL, pretty much every single app is writing wrappers against the OpenSSL API. So if people write wrappers, it's a very strong signal that maybe your API should be changed or improved. So once again, watch what people are building with your APIs, and watch for questions on GitHub, Stack Overflow, and so on. Because once again, what you had in mind may differ from what people actually built, and the question they have might be something that you didn't think about. So this is a bunch of things that you need to clarify or change. And if something is not available and people need it, they're going to reinvent it. Maybe not in a safe way, so just implement it. And it's even the case for very trivial functions. For example, in Sodium, most secret keys are just random numbers. And there's a function to generate random numbers. But in addition to this function to generate random numbers, I recently added something called keygen, which does exactly the same thing. It's essentially an alias. But if you do these kind of very trivial functions, first it improves code clarity. Why does this guy actually generate random numbers? Oh, okay, it's to generate a key. That makes sense now. So it improves code clarity, prevents bugs. It avoids you from having to answer the same questions over and over again. So it's not bloat. It's actually very useful. So these are just some examples from Sodium. All these functions are actually just 1 or 2 lines of code, yet a lot of people use them, and it prevents a bunch of bugs. Still, if you provide only a high abstraction layer, people are going to be like, hey, I want to use this specific function. How do I do it? How do I do it? Well, the thing is, you should expose low-level functions as well, because, well, they are already present in the library, so maybe you should just make them available for people who actually need them. But in the documentation, remain focused on your high-level API. Why? Because people who just need to solve a problem quickly want to take the path of least resistance and use the safest API. And people who know exactly what they are looking for are going to find the functions no matter what. Now, after a while, people are going to ask for specific features. Can you implement this? Can you implement that? I heard about this new sign-in system or this new cipher. Can you add it? Well, if you say yes, you're going to end up with a kitchen sink, very hard to maintain, and very confusing to people. If there are 10 different ways to achieve the same thing, people are going to be totally confused. So the first thing to ask yourself is, does it solve a common problem, not just for one person, impossible to solve currently? So suppose that, yes, there is something that has to be solved and that can't with the current API. But what's the best API to design? So maybe you have something in mind, but maybe people are going to use it in a different way and it's not optimal for them. So one way to do it is to build a different project. And whenever you get a question such as, hey, how do I do that? Redirect people to this other project. Because then, on this project, you can tweak the API according to people's feedback and improve the API according to what people actually need. And after you get something that everybody seems to be happy about, you can actually merge this API back to the main project. So as an example, a lot of people asked, hey, how do I encrypt files with Sodium? And I designed something called blobcrypt, which can write and read encrypted files. You can do random access into files. It's a great API to actually build encrypted file systems. I was really proud of it, but nobody's using it. And the reason for that is that people don't need to build encrypted file systems. People just need to write and read sequential files. So this API was over-engineered for what people actually needed. So watch people use your project and watch yourself use it in your projects as well. Nonce, IVs, are simple in theory. This is just a number that some primitives expect. Essentially, you have to provide a unique number for a given key and message. A new message, poof, a new number. Sounds easy, except that it's actually really tricky to get right, and it's getting worse and worse with cloud computing and everything. So traditionally, crypto libraries require applications to provide a nonce. This is a terrible idea. This is a terrible idea, if only because if you don't do it right, this is what you end up with. So don't do it anymore in any modern crypto library. This API is supposed to manage everything by itself in a safe way. Context separation. So in crypto, you're not supposed to use a key for different things. If you do, bad things can happen. And sometimes it's really not obvious that you actually do it. In OpenBSD, there is a tool called Signify. Signify is used to sign all the packages and the operating system itself. And on a signing machine, Signify stores a hash of the secret key in clear text, which is totally fine, because given the hash, you can't find what the secret key is. But the thing is, the signing algorithm doesn't use the key directly. It uses the hash of the key using the same algorithm. So even if it's not obvious, you're actually using the same key for two different things. And by accident, this is okay here, but it could be a terrible disaster. Should we blame developers? No. Developers don't have to understand how every single primitive works. But API could prevent that. Using something that's been discussed a lot on crypto mailing lists, which is context separation. This is very simple. Whenever you use a key, you just add a small description. This is what I'm going to use this key for. I'm going to use it to hash a username. I'm going to use it to encrypt some message. And if you use the same key in two different contexts, you get a different result. So it prevents this kind of bugs. As of today, no major crypto library actually implements this. This is sad. Key exchange, if you want different parties to communicate, they have to agree on a bunch of secret keys. So this is the key exchange mechanism. Libraries either provide something very simple, such as just a Diffie-Hellman function, and this is usually not enough. You have to do more. Or they can provide a Diffie-Hellman function and tell you what to do with it, and then you have to re-implement everything. It can be even worse in practice. At this point, it's probably safer to just use TLS for key exchange. Or in your library documentation, you can just recommend people to re-implement everything, including TLS. No, that would be terrible. Limitations. You can't use a key forever. You're supposed to switch to a new key quite frequently, or else pretty bad things can happen. And this is something you don't see a lot in the documentation of crypto libraries, but this is something that can hit you really hard. So it really depends on the construction and the cipher and everything, but yeah, you're supposed to rotate key quite frequently. This is annoying. It has huge implications in your protocol designs, in your applications, and this is not something applications should actually worry about. Your API should hide these details and just perform the key rotation itself when it's needed. So, as a proof of concept, I wrote a new library called libhydrogen. So hydrogen initially was designed for a project I was working on Arduinos. So this is really for constrained environments and microcontrollers. And it was a complete rewrite of libstudium with implementation optimized for size. But it was also a good opportunity to totally rethink the API based on lessons from the past and the takeaways from Sodium and modern crypto. So, some key concepts. The crypto in hydrogen is pretty interesting, but this is not the topic today. But it has to be really hard to misuse and consistent. So one example of consistency is that it's using just one key size for everything. If you do hashing, if you do signing, whatever, this is going to be the same key size just to avoid confusion and to avoid bugs by the same way. So maybe because it's the same key size, you're going to reuse a key, right? Well, the thing is, context is mandatory everywhere. So you don't get this kind of bugs as well. And it assumes that the system or hardware can't reliably produce random numbers, which is fairly common in embedded systems. So maybe you're going to have a RNG that spits out just zeros. This is okay. A lot of crypto libraries are going to give you something really insecure, and you can recover the secret key and everything when these kind of things happen. But hydrogen was designed to handle these kind of situations everywhere. And implement only what people actually need and actually use frequently in applications. So as an example of how an API can be used to simplify everything, for hashing, typically you can use a bunch of different functions according to the output size you want, according to the fact that there is a key or not, and this is kind of confusing. So with hydrogen, there is just one function, and under the hood, it's calling the right function according to the output size you need. So the first version of hydrogen was relying on 3 different hash functions, but your high-level API doesn't even know about that. You just have one function to call, and you give it the output size, and it's going to call one of these. And the crypto was completely rewritten in hydrogen version 2, but the API didn't change at all, which is good. Of course, don't ask applications for a nonce. This is a disaster waiting to happen, so just do it in the API transparently. But people who know a little bit about crypto are going to be like, hey, but sometimes if your application can control the nonce, or if you can provide something called additional data, this can be really useful. For example, if I receive a message, I can use this to make sure that this is the message I was waiting for before even decrypting it. Or I can reject all messages based on timestamps, or I can check a version number using this mechanism. Well, let's see how this is used in practice. Or let's reformulate this, but without having a specific cipher in mind, but rather with a typical application in mind. Hey, come on. So what we just expressed before can be expressed that way as well. Check that a value attached to a message is the one we expect. So in your API, just expose this and note all the details. So this is how you encrypt something with hydrogen. You provide a message, a number. Here it's 1. It's a 64-bit number, a context, and a key. And that's it. No nonce. People don't have to know about how to build one and additional data and everything. No, this is handled by the API. Consistency is very important. One more time. For example, there is a construction called HKDF, which is used to derive a bunch of keys based on a master key. And if you read the RFC for HKDF, you're going to read about things such as a sort and key information. Well, in practice, a sort is just a context, as we described before. And a key information can be pretty much anything. It's a vector of bytes. But if you look at actual applications, people just use numbers. Key number 1, key number 2, key number 3. All right. So in your API, don't use a specific vocab. Use the same everywhere. Just call the sort a context. And for the key information, just ask for a key number. Poof, you just hide all the complexity of a specific function. Key exchange. How do we solve the current problem, which is there's nothing in between something really simple but not enough, and TLS? Well, this is what it looks like. You call a function, you get a packet. And then you can do whatever you want with this packet. You're supposed to send it to the peer, so you can use any protocol you want, UDP, TCP, WebSocket, whatever. You just send this packet, and the peer receives this packet, calls a function with this packet, gets a new packet to send back to you. So one more round trip, and poof, you get a very secure key exchange with authentication and ephemeral Diffie-Hellman and everything, but your application doesn't have to worry about these details. Anyway, if you design a novel API, still don't reinvent your crypto. Use something well-studied. You use well-known constructions. So in Hydrogen, I use the noise XXX protocol for key exchange, for example. So that's pretty interesting because a couple of years ago, and if you look even at Wikipedia today, the way people compare crypto libraries is actually by the number of functions available. Like, oh, there's like 50 different hash functions. It has to be good. But in practice, this is just very confusing to people. And it's actually way better to focus on higher level abstraction. It's better for security. It avoids people shooting themselves in the foot. And some key requirements for modern crypto APIs are no limitations, hide all the details, all the limitations of the specific primitives that you're using, misuse resistance, and domain separation. All right, thank you guys. That's all for my talk. And if you want to discuss more about the crypto itself from sodium or hydrogen, I'm available after the talk. Thank you.
Okay.
They were even much quicker to resolve some of the problems that we will report here. So when we gave that to Cisco, the PSER team just responded to us that, well, they would check the business unit, see where the problem is, and they returned to us saying that, well, if they are signed by the same CA, then they can communicate together. Okay, but come on. This shouldn't be. They are from two different domains. As per the RC, it shouldn't be. Well, you know what? We will just add this feature in the future. So just don't complicate it. Okay, I get the point. But, okay, no worries. The problem with this is the following. That if we have a certificate signed by the same CA, we don't check whether you are allowed by the whitelist or not. In other words, there is no mechanism to stop you from connecting to my network. If for any reason the same CA that signed my certificate signed yours, you will always be able to attack my network. Okay, so, you know, I maybe have an idea to resolve such a problem. Maybe I will go to the register here. This is the one responsible for certificates. And usually we can use a command like this. So, I mean, in other words, we can just come here and revoke the certificate. So, at least this certificate won't be valid anymore. When the new device tries to connect to my network, we will check the certificate. We will find out that it's revoked, so they won't be able to join.